balancing a complex redox equation in acidic or basic solution. So the steps that I follow when I solve this kind of problem fall into this basic pattern. So the first step is work out what is being oxidized and what is being reduced. So the easiest way to do that is to look at oxidation states for everything. Um, and then you're going to split into half reactions and balance the half reactions before you put them back together. So when we balance half reactions, the first thing we do is we're going to balance the mass. So let's make sure the number of atoms of each type are the same. And these steps are going to be the same whether we balance in acidic, basic, or neutral solution. And we're just going to ignore oxygens and hydrogens to start with, okay? And then if we're in neutral solution, we can just go straight ahead to the next step, which is balancing charge by adding electrons. But before we do that, if we're in acidic solution, there's a few extra steps we're going to take. And we'll do the same steps for basic as well. So the first step is if there's any oxygen, we're going to balance oxygen with adding water. Okay, and that creates a problem because we may be adding hydrogen that wasn't there before. So we're going to balance hydrogen by adding H plus, okay? And if we are basic only, we're going to do one extra step, which is those H pluses that we added, we're going to balance by adding hydroxide, OH minus, to both sides. And what this will do is H plus plus OH minus will give us water, okay? And then we'll balance the charge of electrons, and that will give you the number of electrons being transferred, which is useful for a lot of chemistry problems. So it's always useful to be mindful of how many electrons are being transferred during the redox process, okay? And then we're going to add the half reactions together. So that is the basic premise of what we do when we balance. So first of all, if I look at this redox reaction here, I can see N2H4 hydrazine. Oh, that's a pretty tough one right there. Hydrogen is usually going to be H plus unless it is bonded to something that is going to be more electropositive, like a metal, forming like a metal hydride. So in this case, I would assume that the hydrogen is a +1 charge, which would make the nitrogen in this compound -2. Okay, so we have +1 and -2. Bromine is just the element, so that'll be 0. Nitrogen is just the elements, that'll be 0. And the bromide ion will be the charge on the ion, which is -1. So hopefully we can see here that we can see our bromine is being reduced right here to from 0 to -1 because reduction is a decrease in oxidation numbers. That's our reduction half reaction. And we can see that hydrogen is only on one side of the equation. So I guess we're just going to ignore that for now. But we can see that nitrogen is going from -2 to 0. So that would correspond to nitrogen being oxidized. So now we know what is going on, we can split up into our two half reactions. So we have our reduction half reaction, which is Br2, and I should be good and leave my state symbols in. Going to Br minus Aq. So looking at this one briefly by itself, I can see right away that the mass is not balanced because I got two bromines on the left and one bromide ion on the right. So I am going to go right ahead and just balance that half reaction before we even get started. And then I should not need to do anything else to that, even though we are in basic solution here, because my bromine is balanced and I don't have to worry about balancing oxygen, hydrogen, etc. The only other thing I would have to do to this is balance the charge because my charge is 0 on the left side and -2 on the right hand side. So I would have to add 2 electrons to this left hand side to make that reduction half reaction balanced. So now I have a net charge of -2 on each side of the arrow. So I can put a pin in that and leave that alone. And that fits with what we understand about reduction oxidation half reaction processes because oxidation is loss of electrons, which means the electron should be on the right hand side of the half reaction, and reduction is gain of electrons, so that means means the electron should be on the left side, the reactant side. Okay, so our oxidation half reaction we can see is going to be a little more complex because we've got the hydrazine N2H4AQ on the left, and then we have our N2 on the right. So our mass of nitrogen is balanced. That's a good place to start, but we can see we have some hydrogen in there. So following through my steps for acidic and basic solution, my mass is balanced except oxygen and hydrogen. I don't have any oxygen to worry about, so I can skip the balancing oxygen with water, but I do need to balance hydrogen by adding H+. So let's go ahead and do that. If I've got 4 hydrogens in the hydrazine molecule on the left-hand side, I'm going to have to add 4 H+ ions to the right-hand side to balance that. And I know we are in basic solution, not acidic solution, but this is just helping us balance it, okay? It's just a means to an end. So now what I've done is I've added H+, but I know I'm actually in basic solution. So to neutralize that H+, I'm going to add hydroxide in order to neutralize that. Now, just like rearranging mathematical equations, what I do to one side, I'm going to do to the other side. So I'm going to add 4 hydroxides to both sides of this equation and promptly run out of space, of course. So what do we have here then? If I've added 4 hydroxides to both sides, and let's put it down here so you can see it. So this H plus and OH minus here is going to combine together because a proton, H plus ion, and hydroxide, OH minus, is going to form water, right? So 4H plus 4OH minus is going to give me 4 waters. And now that will fit. So I can move that back up. So my oxidation half reaction is balanced with regards to mass at this point. The last thing I have to worry about is charge. So we can see on the left-hand side, we have a net charge of -4. So I can balance that by adding 4 electrons to my right-hand side of my equation here. Okay, so now I have a net charge of -4 on each side of my oxidation half reaction. So now these should be ready to balance with respect to each other. Okay, so I can see in my reduction half reaction, I've got 2 electrons, and in my oxidation half reaction, I've got 4 electrons. So the final step then is that I'm going to have to multiply my reduction half reaction by an integer in order to make those balance out. So I would take this whole step and I would multiply it by 2 in order to get this to balance. So I'm going to rewrite my reduction half reaction. So that will be 2Br2 liquid plus 4 electrons. So now we can see that the electrons are going to cancel out. I'm going to move this so we're kind of in the same zone here. Give me 4Br minus AQ. So make sure we do multiply both sides. So then to add these reactions together to make my overall reaction, I'm going to add everything on the left-hand side of the reaction arrow. So overall, I have my hydrazine N2H4AQ. I have my 4OH minus AQ, and I have my 2Br2 liquid. Bromine's one of the 2 elements as liquid at room temperature and pressure. The other one's mercury, of course, and 4 electrons. And these electrons should be cancelling out. Okay, that is your goal to balance your overall redox reaction. And then on the right-hand side, I have N2 gas plus 4 H2O liquid. Oopsie, I can't even type today. That'll teach me for looking at my fingers. 4 H2O liquid plus 4 electrons plus 4Br minus AQ. So hopefully we can see that those electrons are going to cancel out on both sides. So what I can actually do is I can just delete this and delete that, and this will be my overall balanced redox equation as follows. Okay, so that is in basic solution, and we can verify that because we've got excess hydroxide on one side of the reaction.